Okay, um, so the plan for today is to finish up Green's functions, and we might have some time to start Bessel functions, but if we don't, we don't. I built in some extra time so that we can catch up. It's not a big deal if we're essentially a lecture behind the schedule that I put up, so it's kind of built in. So today, so if you remember last time, I kind of introduced the idea of Green's functions, trying to motivate it by something you've seen before, namely Poisson's equation. We're going to dig a little deeper by going to the 1D case and some problems, especially problems that are similar to the two problems that I assigned for your homework, but I think it's a little easier to see where Green's functions come from and why they're important. So that's the goal for today. And I have one simple, not simple, hopefully simple, one example problem for you guys to do that has an answer. So that's why it's simple. It actually works. Regarding announcements for the class, as you know, I hope, your next exam is on Friday, and all the same parameters. That is, it's open book, open notes. You cannot use any internet sources that would allow you to solve differential equations or integrals. But so the only thing online that you should be using is video notes from this class, your own notes. You can use your textbook, obviously. I'll keep my solutions up for the homework. There'll be 4 problems. You can choose which 3. I'll make the test available at 10. It might be even available a little bit earlier. Again, the goal is that it's about an hour-long test, but if you need to take a break and turn it in later, that's fine. Are there any questions about the exam? Okay, make sure you go over the sample exam as you prepare for this. The other thing is, thank you very much. Everybody turned in the homework yesterday, so solutions are available. I'm a little bit behind in the grading, but I will finish up the grading today and tomorrow, hopefully no later than tomorrow morning. But certainly the solutions are there for you to look at. And by tomorrow, I'll have updated your estimated course grades ahead of the midterm, and then I'll grade the midterm over the Memorial Day weekend. Lucky me. And then update your grades. So far, everybody's in great shape. And I haven't dropped any homeworks or anything like that. So everybody's doing great. So under trying circumstances. So well done. Let's get started then. So as I mentioned, today we are going to focus on Green's functions. And I have to tell you, it's taken me 30 years to figure out Green's functions. So if this is confusing, it's because it's confusing. But as I was preparing the lecture, I think I finally got it. And I've taught this course 3 times. So, but now I think I really get it. And what it comes down to, I did some digging because we have so much time now, about where it comes historically. And where historically the Green's function comes from is basically trying to model what happens when you have an impulsive drive to basically the trajectory of something. It's an impulse reaction to a differential equation. So you can think of, as I've drawn in the figure, essentially the kind of thing that you would imagine the impulse approximation. You have something moving in a straight line from infinity, and it gets one sharp force at a particular point, say x equals t. And then we've done, in fact, it was a problem in, I don't know, maybe the 2nd chapter of the Green book in computational mechanics. You may not remember it, but this is a problem that we can solve. But hidden in that is the origin of the Green's function, or Green's functions, namely that impulsive reaction can be modeled as a delta function. And essentially that's the origin of the Green's functions. Typically what we're looking at in terms of what we're concerned about is that we can take this idea of how an impulsive reaction occurs with the trajectory of something and apply that to a differential equation that has an impulsive, we can call it an impulsive, non-homogeneous function. That is, we can take a differential equation that's homogeneous and treat the particular part of it, the y sub p, the function, on the other side of the operator as this impulse. And that's why you'll see in chapter 10, for example, that we're looking at Green's functions from x less than t and x greater than t, because of basically what we're doing is looking at differential equations on a domain, say a and b, and sometimes that a and b can be infinite. We'll start with the case where they're homogeneous, that is a and b are the same value, or the boundary conditions are the same value, and then move from there. Okay, so that in essence explains where that came from. The other part to that is what I did last time, which is taking the pieces out of Poisson's equation and realizing that the charge density is actually which is the inhomogeneous part of the differential equation, is actually inside the solution. It's a weight or a kernel inside the integral equation. We'll get to that in a bit. All right, so with that historical aside, let's consider our standard linear differential operator. So say L operating on y, that would be, say, d dx, p of x, d dx, plus q of x in the most general term, operating on y of x. And we're going to set that equal to f of x, which is not equal to 0. Right, so we've gone over a number of cases on how you solve this when y is equal to 0. Now we want to look at the case when f of x is not equal, or is equal to 0. And we're defining this on the interval between a and b. What I sort of proposed or stated last time is that this operator acting on a function that we'll call g as a function of x and t is equal to the delta function x minus t. And given that, what that means is that the particular solution for y of x for b.1 is the integral from a to b of whatever this function is times whatever the inhomogeneous part of the differential equation is. In other words, we've spent the good part of 2 weeks solving homogeneous partial differential equations and even ordinary differential equations. The whole point behind a Green's function, or the Green's functions, is to solve the non-homogeneous differential equations. And the way you solve it is identifying what this impulse is, and then this Green's function times that inhomogeneous part in the integral. And if that turns out to be an integral that you can solve, great, gives you that particular solution. All right, so let's see. So that's the setup. The form, and again, we're looking at the case in 1D. So again, we're going to look at, how are we going to do this? G of x and t being equal to some solution y1 of x times a weight h1 of t for x less than t, and g of x t equal to another solution y2 of x times h2 of t for x greater than t. Again, what you should be thinking about is you have some domain, and it doesn't have to be equally split. There is some point t, right, where x is less than t, x is greater than t, and our y1 matches the boundary condition at that first point. Y2 matches the boundary condition at the other point. That'll help us decide which one of these solutions is y1 and y2. The other part to this is that y1 of x is the solution to a homogeneous equation. In other words, L times y1 of x is equal to 0 at A. That's another way of saying that it matches the boundary condition for the homogeneous differential equation. So if we were doing this for the Poisson equation, right? Y1 would be the solution to Laplace's equation at x equals A, right? And Y2 would be the solution to Laplace's equation at point x equals B. Okay. Is everybody with me so far? Give a thumbs up. Or a question. All right. So all we're doing is trying to divide this up. And again, this doesn't have to be equally divided. We're just marking out y1 solves the homogeneous equation at one point, y2 solves it at the other point. The question then is, what are these weights, right? We want to generate the Green's function. The Green's function isn't the solution. It's the weight or the kernel that goes inside the integral that does provide us the solution. And so the way to write this goes back to the Wronskian. And rather than go through the derivation, which takes about 2 pages in your book, I'm just going to state that the general case for Green's function is equal to some normalization constant A times y1 of x, y2 of t for x less than t, and that same constant times y2 of x times y1 of t for x greater than t. Okay, and again, just think of t as a parameter or spot that cuts off these two solutions at the endpoints. Because it's going to be a little confusing when we start doing the intervals, but it's a way of us just splitting apart the solution into these two pieces. The way we get A is basically looking at the Wronskian of these two solutions. In other words, if we go back to the original definition of the Wronskian, we can write that A for any of these Green's function is equal to 1 over P of t times y2 prime of t, y1 of t, minus y1 prime of t, y2 of t to the minus 1. Right? And our goal should be with every one of these equations to find that A. Right? And that allows us to solve for the Green's function. Basically, our steps are, so we'll do a couple of examples. The steps are identify what we're dealing with for the homogeneous case. So that's step 1. 2, find A. 3, combine to get g of x t in both the region x less than t and x greater than t. And then ultimately 4 would be solved for y sub p, but in order to do that, we need f of x. Okay, so our first goal with Green's function is just to find the function, right? Find that impulse to the differential equation. And then the really cool thing about Green's functions, the thing that really makes it kind of magic, is that once you find the Green function for a differential operator, you've done all the work you need to do. It's true for every problem with that differential operator. As we'll see, the Green's function for Poisson's equation, for the Laplace equation, Poisson's equation, in 1D, 2D, and 3D has a very specific form, and you can apply that to every single Poisson equation, no matter what f of x is equal to. Same thing for the Helmholtz, the modified Helmholtz, all of these partial differential, the wave equation, all of these partial differential equations, once you know what the Green's function is, you have a pathway to solving the non-homogeneous partial differential equation, which is really cool. Now, it might be that you get an integral that you can't do, but fortunately, that's what Wolfram is for. So anyway, let's look at a specific example. Let's look at, so this is example 1. Minus y double prime is equal to f of x with the boundary conditions y of 0 is equal to y of 1 is equal to 0. Okay, so a fairly straightforward problem in that our first step is to identify what the homogeneous equation is, right? So we go with step 1. We want to know what that is. Well, that is just y double prime of x is equal to 0. Again, in one dimension, right? So what's the solution for this? We'll call this y sub 0, since this is the homogeneous term. What is the general solution for that?
Linear.
Yeah, so it's a linear equation, and we can write that as C0 plus a C1 x, right? Then our next step is to find a. In order to find a, we need to find, so this is kind of step 1a, I guess, or step 2a, is we want to know what y1 and y2 are. And remember, y1 and y2 solve the homogeneous equation at A and at B. So we have the boundary conditions up here, right? So our A and B, A is equal to 0, B is equal to 1, right? So that means that y1 is equal to x, okay? If we look at that equation and we put in x equals 0, then y1 satisfies f of 0 equals 0. On the other hand, y2 is 1 minus x. This satisfies that. Okay. The only other piece then that we need for solving for a is identifying what p of x is, but that is minus 1. That's just up here. Okay. So now we're in a position to find a. A is equal to 1 over minus 1 times, I'll get this right now, minus 1 times x minus 1 times 1 minus x to the minus 1. That is, we're taking the derivative times the solution, and then the derivative times the solution, right? And if we plug through that, we should get 1. So our normalization is just 1. Sometimes it'll depend on x, right? But we're happily, in this case, it's just equal to 1. That means that g of x t is equal to x times 1 minus t for x between 0 and t, and equal to t minus 1 times 1 minus x for x between t and 1. Okay. Now, this is true for that linear operator no matter what f of x is. We can't do anything else until we know what f of x is. But we have what our y1 and y2 are. We now know what a is. Right? And given that, we can write that the, let's see, let's let f of x equal sine pi x on the interval 0 to 1. Then as a specific example. This is where it gets a little bit hairy because we want to kind of transform these integrals over t because we're trying to find a functional form. So this integral, 0 to 1 of g of x t times sine pi t dt is now equal to breaking up this integral into 2 pieces. And this is why it gets a little hairy. We're trying to find the functional form of x. So actually, give me a little space here. Oops. We have 1 minus x times the integral from 0 to x of t times sine pi t dt. In other words, we're kind of replacing the t and the x in order to make this integral a functional form rather than evaluating it for a number. And you'll do this every time you use a Green's function. Plus x now times the integral from x to 1 of 1 minus t sine pi t dt. Right? This is what our f of x is. This is our value of x that goes in the interval. And if you evaluate all of this, ultimately you get 1 over pi squared sine pi x. In other words, the interval minus y double, or the differential equation minus y double prime is equal to sine pi x has the solution y of x is equal to 1 over pi squared sine pi x with the BC's given. Okay, so what we did was we took the differential equation, looked at what the homogeneous form was, found 2 solutions that match the boundary conditions, normalized them. That gives us our Green's function. Once we've got our Green's function, we need to know what f of x is. Right? If we don't have f of x, we're done. If we have f of x, then we have to do one more integral. Okay? I'm going to stop and see if you have any questions.
So t is like completely arbitrary. It's just sort of like a dummy variable that goes into all this.
Exactly. It is just something that's a variable that cuts off the 2 different solutions at the boundaries. Exactly. And that's why we're integrating over t, because what we want eventually is a function of x. Yep. And I apologize because your book is not very clear on this, and it starts swapping t's and x's around. Even though we find these Green functions in terms of t and x, we kind of flip it around when we do the interval. This is why it took me 30 years to figure this out. Or so. All right. Let's do one more example. And then if there are no more questions. Okay, so example 2. Here we can look at non-homogeneous boundary condition. What do we do here? And these can take a lot of different forms. They can be that they're not the same, right? They're not tied to the same value, or they don't exist on one end of the differential equation. So here we're going to consider Ly is equal to d squared dx squared plus 1 y is equal to f of x, with y of 0 equal to 0 and y prime of 0 equal to 0. You notice right away we have a problem, right? We don't have the other endpoint, right? We don't have a boundary condition on the other endpoint, say at y equals 1. We only have the boundary condition for y prime of 0. And the reason why I bring this up is because if you look at the development of this impulse, basically development of Green's function, there's a discontinuity in the solution and in Green's function, such that in the limit, basically as x approaches t, we have dg dx from, say, t plus minus dg dx from t minus goes to 1 over p. This is v10. In other words, if you think about wherever t is, right, you can approach it from either side, and that the difference of the derivatives as you get closer and closer should approach 1 over p. The reason for that becomes maybe a little clearer when we do an example. In this case, step 1, we want to identify the homogeneous case. So that's Ly is equal to 0. Okay. That means that y1 is sine of x, right? That's the one that satisfies the boundary at x equals 0. That means that even though we don't have that other boundary, the other solution has to be cosine of x, just from the differential equation, right? So what do? We have g of x t is going to be equal to some constant c1 of t times y1 plus c2 of t times y2. That's because g of x and t is equal to 0 for x less than t. From the setup of the problem and from what we have, what we're given in the problem, we already know part of the Green's function. So we need to find the other part. So we're left with, say, a linear combination of these two solutions. This can be written as c1 of t times sine of x plus c2 of t times cosine of x. We don't have any boundary conditions. So the only thing that we can do is look at the join between these solutions, or the join of Green's function as we approach t. In other words, g, let's say, as x is approaching t from the negative side, it's a function of t. If it's continuous, that is, it approaches the same value on the other side, that means that sine 1 or c1 sine of t plus c2 cosine of t is going to be equal to 0. Right? They're going to approach the same thing. We have dg dx evaluated at, here, let me write this. On the plus side, minus dg dx. On the minus side, equals 1 over p equals 1. So that means that c1 cosine t minus, c2 sine t is equal to 1. We've taken the derivative, right, of g with respect to x on either side. For this to be equal to 1, right, and this is where it can be a little tricky, we know what c1 and c2 are. Remember, they're functions of this parameter t. So what does c1 of t have to be equal to? Or what is the combination? What's the hint here? If c1 times cosine of 2 minus c2 times sine of t is equal to 1, what do we know whenever we see cosines and sines and 1 on the other side? What should be
Pythagorean identity.
Right. We want to make this cosine squared times sine squared, right? That would certainly be a solution. So in this case, this would mean that c1 would be cosine of t, and c2 would be minus sine t. That would certainly make this discontinuity condition valid. And that leads to cosine squared t plus sine squared t equal to 1. That means that we have g of xt, again on the plus side, equal to cosine t sine of x minus sine t cosine of x. But we can use an angle identity. You can certainly leave it like this, but it is a little easier to combine that as x minus t. And so we have g of xt is equal to 0 on the minus side, and sine of x minus t for x greater than t. So in other words, this again would be the Green's function for the differential equation for this specific differential equation, no matter what f of x is. We're not actually solving what f of x is or y of p, right? Most of the battle is trying to find our g of x or g of xt using those steps. Okay? Any questions? Yes, Allie.
Okay, what do you do if the C1 and C2s aren't as apparent? Because I feel like this example, it's pretty obvious like what it would be, but I feel like we're gonna have homework questions where it's not.
Mm-hmm. So some of that is practice, but often what happens, so in this is a case where there's this join because there's no boundary condition. Those are generally harder. We're going to do an example now that maybe gets at this, where there are boundary conditions, but they're boundary conditions at infinity. Okay. The general case that, basically, if we go way back up to here, right? I mean, this is true, right? So you've done most of the work. The trick is then trying to find what that in this case the C1 and C2 are. That does make it a trickier problem. Often, though, we have boundary conditions, either boundary conditions that go to infinity or boundary conditions that we can deal with. If I were to ever ask you something like this, I would direct you, because this is the first time you're doing this. Okay? All right. All right, so it's time for the in-class problem then. The in-class problem is the following. We're going to consider the Helmholtz equation. All right, so the Helmholtz equation is d squared dx squared psi of x minus k squared psi of x equals f of x. All right, and the conditions are that as x goes to infinity, psi goes to 0. As x goes to minus infinity, psi goes to 0. Okay, so you are to, in your groups, use the steps. That is, identify L psi equals 0. Find y1, y2, which means finding A, which means then finding ultimately g of xt, given these conditions. These are a little bit different than what we've been doing so far in that the boundaries now are at infinity, right? So you're gonna have one solution that matches the homogeneous equation at x equals minus infinity and one that matches it at x equals infinity. Okay? Thumbs up if you understand what you need to be doing-ish. Okay. All right, let's get to it then. And here we go. All right, away you go. How'd you guys do?
Found the green function.
What's that?
We found our G, our big
Okay.
Mhm.
What'd you get?
we got for x less than t, we got negative 1 over 2k e to the kx times e to the minus kt.
Mhm.
And for x greater than t, negative 1 over 2k e to the minus kx times e to the kt.
Perfect.
Cool.
Yep.
So for the C of T's, the C1 of T and the C2 of T, is that only for when there's no boundary conditions?
Right.
Okay.
Yeah, that's where you're trying to match the Green's function at that joining point using that discontinuity in the
Okay.
derivatives because you don't have that other boundary condition. Yep.
Okay.
So it's kind of rare because most of the time we have those boundary conditions. We might have you might see it when there's like a time dependent differential equation that has an initial condition, right? But no final condition.
Okay.
Good. All right, let me give these guys one minute.
I've almost packed everything in my life.
Yeah? When are you going? Right after?
Saturday. Saturday,
Okay.
Where are you going?
LA.
Is that for grad school? Damn, you're leaving early.
Mm-hmm.
Our rent's up here, so
Mhm.
gotta go. Yeah, I have nothing.
How'd you guys do?
Good.
Combination of exponentials.
Yes.
There you go.
Oh.
Ah. Mm-mm. Everybody back? There we go. Okay, so hopefully what you found, it sounds like at least a couple of groups saw this, is that for the given conditions, your y1 of x would be equal to e to the kx. That solves the negative infinity boundary condition. Y2 of x would be equal to e to the minus kx. And we know that p is equal to 1. So solving for a, you should have gotten 1 over minus 2k. That just comes from the derivatives of these two functions. And so ultimately your Green's function should look like minus 1 over 2k times e to the minus kt e to the kx for x greater than t, and minus 1 over 2k just the other way around, e to the kt e to the minus kx for x less than t. Or one way of combining all of this would be that g of xt is equal to 1 or minus 1 over 2k times e to the k x minus t absolute value. Okay, So that is the one-dimensional solution to the Green's function for the Helmholtz differential equation. And in fact, now that you have this, if you were given the Helmholtz equation and you needed to find, and you're given f of x so that it's non-homogeneous, you have a pathway to solving that equation. And in fact, the last thing that I'll leave you with are sample Green's functions. Namely, you can have for the different differential operators, say del squared plus k squared, and del squared minus k squared, which is what you just did. And because these take on different characteristics, you can look at what these all look like in 1 and 2 and 3 dimensions. So we've done some of this already. Say, for example, in 2D, the Laplace operator has minus 1 over 2 pi times the log of rho 1 minus rho 2. In 3D, which is where we started all of this, 1 over 4 pi over R1 minus R2. The modified Helmholtz equation, which is plus k squared, is very similar to the Helmholtz equation. It's just that the exponential, the argument, you can tell, would be cosines and sines, or another way to make that compactly is an imaginary argument for, say, x1 minus x2. And here we're using a different way of writing the Green's functions, where we're identifying x1 and x2. This is where we can replace that t, and we can, if you think about how we first developed this, we looked at how a source charge at, say, R2 would affect something charge at R1. So we're changing our t's to basically x1s in this case. And you just solve this guy over 2k e xp, actually 2p exp to the minus k x1 minus x2. What's interesting, and you can look up the solutions here, but you can imagine that they're essentially combinations of what we find here and what we found up here, namely a 1 over 4 pi, and then these exponential terms. What we're going to focus on next week is what happens right here. And the Green's functions for the modified and the regular Helmholtz equations are Hankel and Bessel functions. And so next week, when we come back from the weekend and the exam, we'll start looking at what do these specialized functions, how do they behave, how do we use them, what solutions, these are series solutions for different geometries for different differential operators. But now we have the tools in our toolkit to at least assemble a solution for non-homogeneous partial differential equations, which is awesome. I think that's really cool. And it's actually not too bad. It's, like I said in the email, it's a little bit like spooky magic. It's sort of like, I'm going to assume the answer, and this is the answer. So, good luck. I have office hours. I'll have another set of office hours on Thursday from, see, I have an independent study at 3. So from 2 to 3 on Thursday, if you have any last minute questions, ping me or drop by and I'll be available. Otherwise, ping me if you have questions. And good luck. You guys are going to be great on Friday. Do the sample exam and then have a great, safe weekend. Okay? All right. Bye, guys.
Bye, thanks.
Bye, Willow.
Bye, Allie.